Okay, so this is lecture 17, lecture number 17, Physics 112. So I'm going to talk about something called capacitors and dielectrics, and the section is section 19.5, that is chapter 19, section 5, okay? So I'm going to talk about capacitors first. So a capacitor is, in simplest terms, is nothing but a charge storing device, okay? So one of the simplest form is what we call the parallel plates. Parallel plates capacitor. And the reason is because it's made out of two plates that are parallel to each other. And one is connected to the positive terminal of a battery, and one is connected to the negative terminal of the battery. So this is your battery, okay? And let's say the distance between them is d, okay? So then you have a parallel plate capacitor, and this is made out of metal. And so you have positive charge Q and negative charge Q on these plates. So then we'll say that this capacitor will store charge Q, although the net charge is 0. We always say it is positive some number Q, right? So it stores, let's say, like 1 coulomb charge, okay? Actually, 1 coulomb is a very large amount of charge. I'm just giving you an example. All right. So, first of all, how much charge can these things store? So we want to find out how much charge they can store. And obviously, one thing we know is when we have positive charge and negative charge on these plates, then there'll be electric field going from positive plates to negative plate, right? So we know that that's electric field going in that direction, and these are negative charges. This is a negative plate, positive plate. And so we know that electric field E is proportional to the amount of charge you have on these plates Q. So the more you have charge on these plates, then the stronger the electric field will be. So E is directly proportional to Q. But we also know that when you have two plates, and let's say the distance between them is d, the potential difference between these plates, we call it V. Remember, V is equal to E times D, right? E is the electric field in between, and D is the distance. Then the voltage difference is given by V is equal to E times D. So obviously, E is proportional to V. Therefore, obviously, we know that E is also proportional to V. So E is proportional to V, Q is proportional to E, so Q must be proportional to V. So then we simply get a relation, Q is proportional to V. All right? Now, whenever you have a proportionality, then we can always make it into an equal sign and make it an equation. And in order to do that, we have to put a proportionality constant. So we call that constant C, and C is your, what you call the capacitance. Capacitance. Capacitance of this parallel plate capacitor. Okay? And the units is simply C is equal to Q by V. So Q is given in terms of coulomb, and V is given in terms of volts. unfortunately, voltage, the unit for voltage is also written V. So the unit for capacitance is coulomb per volt. Now, there is a shorter notation for that. Coulomb per volt is called farad. So 1 farad, which is short for Faraday, Michael Faraday, British physicist. Oh, I spelled it wrong, sorry. Right, 1 farad is equal to 1 coulomb divided by 1 volt. Okay, so 1 coulomb per volt is equal to 1 farad. All right, so you will see we use nanofarad, microfarad, and also picofarad. This is 10 to the power minus 9. Micro is 10 to the negative 6. Pico is 10 to the negative 12. Okay, so you can always check. Now, there is another way to write the capacitance of a parallel plate capacitor, and that is C is equal to epsilon naught A by D, where A is the area of the plate. So this is the area of the plate, A. D is the distance between these two plates. So this is distance D. And the constant epsilon naught is called the permittivity of free space. And it's numerically equal to 8.85 times 10 to the power minus 12 farad per meter. Okay, that's epsilon naught. Later you will see that there's another constant called mu naught. That mu naught and epsilon naught are very interesting constants because by knowing that you can find the velocity of light. But still we're ahead of ourselves. So this is permittivity of free space. So now we have two formulas. One is C is equal to Q by V. That's for a capacitor. In general, that is, you can store Q amount of charge and the voltage difference is V. Then C is equal to Q by V. For parallel plates capacitor, now this is specifically only for parallel plates capacitors, then C is also can be written as epsilon naught A by D, where A is the area and D is the separation distance between the plates. Alright? So of course A is in meters squared and D is in meters. Alright? So we have two formulas now. So let me go to another page. So let me call it page 2. So in this one, I'm going to do exercise 19.8. Let me put it underneath so I can find better. Otherwise, I can feel the table. So the question is two parts. It has part A. You have parallel plate capacitor. A is equal to 1 meter squared. So area of the plate is 1 meter squared. And the two plates are separated by distance D is equal to 1 millimeter. So millimeter is 10 to the power negative 3 meters. Okay, centimeter, remember, was 10 to the negative 2. For millimeter, we multiply by 10 to the negative 3 to get into meters. Okay, and we want, and the two plates in between is air. So if you look at the book, you will see that epsilon naught for vacuum is that number that I told you, 8.85 times 10 to the power minus 12 farads per meter. And for air or dry air, it's also very, very close to that number. So for dry air or vacuum, then we are going to use this number. Epsilon naught is equal to 8.585 times 10 to the negative 12 farad per meter. So then in that case, what will be the capacitance? That's very simple. C is equal to Q by V. That's one formula. Obviously, I don't have Q, I don't have V, but I have for parallel plates capacitor, I have another formula. C is equal to epsilon naught A by D. That's the second formula that we talk about. So I'm going to use this one. Okay. So C is equal to epsilon naught is 8.85. So don't use the wrong formula and say, oh no, the problem is wrong, I don't know anything. So make sure you use the right one. 8.85 times 10 to the power minus 12 farad per meter. And then I have A. A is 1 meter squared. So I just put 1 meter squared divided by D, which is equal to 1 millimeter. So 1 times 10 to the negative 3. So 1 times 10 to the power negative 3 meters. So if you look at that, meter square, this is meter, meter, meter square at the bottom, so they cancel out. So the answer will be in farad, and this is 10 to the power negative 3, this is 10 to the power negative 12, so the answer is 8.85 times 10 to the power minus 9 farad, which is equal to 8.85 8.85 nanofarad, right? 10 to the negative 9 is nano. So 10 to the power negative 9 is nano. 10 to the power negative 6 will be micro. 10 to the power minus 12 will be pico. Okay? All right. Now, for part B, the question is the voltage difference between the two plates V is given as 3 times 10 to the power 3 volts. Okay? So that's quite a bit of voltage, 3000 volts. And how much charge this capacitor is storing? That means you need to find the amount of charge you have on one of these plates. I want to find Q. So by the way, look at this. I write V is equal to 3 times 10 to the power 3 volt, but actually it's volt, right? But usually volt, the unit for volt is also V. So we have to be careful when you write also, and don't go cancel this V and this V, all right? So that will be funny. And then now, what about our capacitance? C is equal to Q by V. So we want to find Q, therefore Q is equal to C times V. But we already know what C is from above. Therefore Q is equal to, C is 8.85 times nanofarad, 10 to the power negative 9 farad, and V is 3 times 10 to the power 3 volts. So if I multiply it out, the answer is 26.6 times 10 to the power negative 6, because minus 9 and plus 3 I get negative 6 farad. Coulomb, because farad times volt, So I'll get Coulomb because Farad is volt, Coulomb per volt, right? Farad in units, I write with the square brackets so you'll know in units, is Coulomb per volt. So volt and volt cancel out, so I get Coulomb. And so that is 26.6 microcoulomb. That's your charge. Oh, so that's your charge. Now there's one more thing I need to talk about, and that is dielectric. Okay, so I'll talk about it in another lecture because now the video is getting long. I don't want to do it more than 15 minutes, so we'll quit here for this one. See you in the next one.